So we've learned a lot about impulse at this point. The idea that we can directly relate information about force and the time that force is applied and figure out how an object's velocity changes is pretty cool. It helps us understand how for a certain change in momentum, like a car crash, that you have a choice between applying a small force for a long time or a large force for a short time. There's another great thing you can do with impulse as well. And the reason this is so valuable is that we often can't directly calculate impulse because forces are complicated. This happens mostly in collisions and explosions. If a cannon is shooting a cannonball, the force on the ball is going to be varied as it moves down the bore. It's going to be moving away from the explosion, and that means the force is going to be changing. In a car crash, as the two hit each other, the force is relatively small at first, but as they start to crumple into each other, it's going to increase rapidly. And we might not have any way of quantifying those forces. But by looking at how motion changes and using the idea of impulse and Newton's third law, we can still find out a lot about them. So what do I mean by that? You remember from Newton's third law that if object A puts a force on B, B puts the same force back on A. That implies that the impulses the two objects give are equal because they're putting the same force on each other during the same time. That implies that the change in momentum of the two objects are equal. And that means we can write force out of the equation entirely. It's important, it's there, but we don't have to look at it. We can just look at changes in motion of the objects. That's not all that impressive when it's a simple system. So I'm going to have an explosion here. I've got two identical carts. They're put together. There's a spring-loaded plunger between them. And when I release the spring, I think you know what's going to happen. They travel about the same distance. And that's not surprising because there's some symmetry here. We could have predicted that. But it becomes a lot more interesting when we don't have symmetry. So we'll set it back up, and we'll change one thing. We'll put one of the kilogram masses onto this cart. You might be able to predict what's going to happen using Newton's third law. But there's actually a numerical relationship to describe just how much farther that one went than this one. That's what momentum is going to help us do. As we increase the difference between the two objects and decrease the symmetry, the situation becomes a lot more extreme. One object moves a lot more than the other. Being able to predict precisely how much more is really important if, for example, what you're designing here is a cannon or a gun. You want one of the objects to move a lot more than the other. So in the next unit, we're going to figure out how does the motion of these two carts related using the ideas of momentum.